which means it's Cauchy. So Cauchy sequences converge, and convergent sequences are Cauchy in the real number system. So now we have that one going both ways. Remember that. That's an important third one.
Say it again, Cauchy sequences converge.
A Cauchy sequence of reals converges if and only if the sequence converges. If you want me to break that apart, say a Cauchy sequence is convergent, that's part one, and a convergent sequence is Cauchy, that's part two. And it all hinges on the completeness of the reals. Those statements would be untrue for rationals. Why? Because just when you think you're going to get the limit, it turns out it's irrational. It can jump out of your little system. But not with real numbers. If you're headed toward a limit, it's there. It's like the roadblock is really there. No mirages. No holes. All right. Let's turn this around. Let's turn this around. Let's do one more thing. Then we'll pick this up again on Tuesday. We'll have lots of stuff to do. And we'll try to hammer. If you can read a little bit of chapter 3, we'll hammer the very final thing on Cauchy here with and we'll do the Riemann integral as well. Because they'll be very similar. Now that we've fought our way through all the details of Cauchy, the Riemann thing will go very smoothly. So what we're doing here is establishing the basis to conclude that those sums for the partitions actually converge somewhere, right? Okay, one last factor. We have shown that a convergent sequence is Cauchy. Let's prove, using some of the machinery that we already have, that a Cauchy sequence is convergent. Remember, it's these sums, these Cauchy sums that are coming out of our integral representation. They have to converge. How about can we prove that a Cauchy sequence is convergent? We said so. We said, well, the real numbers are complete. That's why they're convergent. But okay, can we prove that? Well, given a Cauchy sequence, xn, for pre-signed epsilon greater than 0, there exists an n of epsilon such that whenever p and q are greater than that n of epsilon, it follows that x of p and x of q are absolutely no further apart than epsilon. Choose epsilon equal to 1. Then there exists an n of 1. So whenever p and q are mutually greater than n of 1, it follows that x of p minus x of q are less than 1. Okay. Now, I claim that the set x sub n is bounded. Here's why. Here's x1. Here's x2. Here's x3. Blah, blah, blah. I finally get to x sub n of 1. Okay? This is a finite number of points up to this guy, right? Where's everybody else? Well, I think actually we have to go as one more bit. We have to find x sub n of 1 plus 1, right? Because we're greater than n of 1. And everybody else is within 1. You know, let p equal n of 1 plus 1. Then everybody else is within 1 of him. So then I go on either side of this guy, 1 unit. And I have a finite number of points out here, and then infinitely many within 1 of this particular x. So what do we have here? Is this a bounded set? It's a bounded set. Is it an infinite set? What do we know about bounded infinite sets? Well, we have one. That's the Bolzano-Weiss stress theorem. Bounded infinite set of real numbers by the Bolzano-Weiss stress theorem. That's the limit. Right? Look in your notes again. That's what's going to be it. Bolzano-Weiss stress theorem says if you ever can find infinitely many real numbers that all sit in somebody given, as they are doing here, somewhere over the rainbow there's a lambda, which is a limit point. Okay? All right. I claim this Cauchy sequence converges to lambda. It's not only a limit point, it's stronger than that. It's a limit. Well, here, I'll just give you the informal argument. How can it not be? If infinitely many of the xn's are arbitrarily close to lambda, and then once I get far enough out, they're arbitrarily close to each other, how far can they stray from lambda? Not too damn far, right? They're all mutually close, and they're all pretty close to lambda, right? So I claim the distance between any one of them from lambda is controllably small. But what does that mean? Do they converge to lambda? So using Bolzano-Weierstrass, I have the flip of that, the converse of that statement. So every Cauchy sequence of reals converges, and every convergent sequence is Cauchy. So we have now some basis for saying that the sequence of sums, the Cauchy sums, that our integral is built on. Those things all are going somewhere to a common place, and that will turn out to be the Cauchy integral. Okay? So we needed this scaffolding really put up so that we could get a handle on what the main building's going to look like. All right? So let's read a little bit of chapter 3. We'll finish this on Tuesday. Wendy's going to start with the Lebesgue number existing and show Heine. Bill's going to show that the Lebesgue number for an arbitrary open cover compact set exists.